Yeah, thank you for sticking around for the last talk of the day. This is different from the title that is in the program. I deleted the word anomalous because I didn't want to be too controversial. So just explicitly wrote exactly what I mean. This is work with Wilbur, Wenjie, and Michael. Wenjie is in the audience. You guys know everybody in this list. Right. So as Ruben showed in his presentation a couple weeks ago, there are many different definitions of 't Hooft anomaly in the literature and in the community. The two most popular ones from his survey were obstruction to gauging symmetry and obstruction to a trivially gapped symmetric phase, or an SPT. And even though this is a very old topic, there are still lots of recent work talking about the subtleties of different definitions of anomaly, and also comparing these two definitions of anomaly, especially in the context of generalized symmetry. There was some relevant, very, very recent work by Sahan and Wilbur that showed that in 1+1D at least, these two definitions are the same. The main point of today's talk is to show that these two definitions are not the same in 2+1D. And to tell you exactly the setting that we're going to consider, it's going to be in lattice models, and when I say locality preserving, it's really the strict locality. So when I say operator is locality preserving, it takes local operators to strictly local operators. And I might mention at the end some generalizations. Again, it's in 2+1D, and we're going to consider finite dimensional ancillas. I'll tell you exactly where ancillas come into play. But this is the exact setting that we're going to consider. And the symmetries that we're going to consider are the most vanilla possible kinds of symmetries you can have. So linear, no time reversal symmetry. Internal symmetry, so they don't depend on the crystal structure. They don't take operators to very far away operators. Finite, invertible, zero-form symmetries, the most vanilla type of symmetry. And in this context, what we find is that there are examples of non-onsiteable, not gaugeable symmetries. You can't even really couple them to background gauge fields, let alone dynamical ones, that nevertheless admit trivially symmetric states, in particular product states. And Dominic Else and collaborators also has somewhat related work. Okay, so let me just, yes.
So a trivial corollary seems to be that you are saying that the obstruction to gauging is not RG invariant?
This is specifically going to be in lattice models. So there will be some things that are more difficult to say how this generalizes to continuum field theory that you might find.
Okay.
Yeah.
Sorry, just a question about English. When you say it's non-onsiteable and non-gaugeable, does that mean both can't happen together or neither can happen?
You can't have either.
Either.
Yeah.
Okay.
Okay. So the main results that we have is we have an index for 2D symmetries with all of the definitions that we had previously. Taking value in H2 of G with coefficients in the rational numbers under multiplication. This might look weird. This is related to the group of quantum cellular automata, QCA and 1+1D. So I'll show exactly how that arises later on. This is an index that we can compute for any 2D internal unitary finite symmetry. And we have a proof that this index must be trivial for onsiteable gaugeable symmetries. And for every element in this, every omega, we can construct a fixed point kind of set of symmetry operators. And the set of symmetry operators come equipped with a symmetric product state, a symmetric computing parent Hamiltonian for this product state, and also a corresponding 3+1D G symmetry protected quantum cellular automata. So the symmetry here is G, so it's a G protected quantum cellular automata in one higher dimension, so in 3+1D. Okay. Before I get into our construction, I'll just tell you very briefly about the inspiration. And this will be brief because the construction that we have makes the things we want to prove a bit more transparent. But we were inspired by this work back in 2017 called the radical Floquet circuit. It's a finite depth circuit in 2 plus 1D, and it has some intriguing properties. So its fourth power is 1, so you can call it a Z4 symmetry. It's locality preserving, its fourth power is 1. The torque code ground state is invariant under this operator, and in fact it permutes the E and M string operators, so it implements an EM permutation on the torque code ground state. And if you restrict this circuit to a patch, say A, and you take it to the fourth power, it gives you a translation of a qubit square. And we'll show that's related to the fact that it's not possible to make this on-site, the symmetry on-site. And there is also a classification of Z4 anomalies in 2 plus 1D. There are no anomalies in 2 plus 1D by group cohomology or by cobordism. So this kind of on-siteability cannot be explained by the anomaly calculation in those ways. The H3 class is trivial, particular. Why is the squaring to a translation to the fourth power giving you a square of translation strange? If I take an on-site Z4 symmetry, I can always restrict it to a patch in the obvious way, which is I just take, by on-site just means that it's a product of local unitaries, and each of them is supported on a site. If I want to restrict it to A, I just take the product that are in A. And whenever we have a local unitary operator, there's an ambiguity of how to truncate this operator. So that's this U partial A here. We can kind of dress this boundary by any locality preserving unitary that's only supported on the boundary. It doesn't change the bulk action. And these kinds of locality preserving unitaries are classified. They are generalized translations for this kind of Hilbert space. They take value in 2 to the n, basically the number of qubits that are translated along this edge. And this index I will explain in more detail shortly. So that means that if I take this guy to the fourth power, I will always get 4 times the translation up to a finite depth circuit along the boundary. So then it's very strange that this guy to the fourth power gives you translation square. So then this is not on-site, and if you work a bit harder, you'll show that it's not actually equivalent to an on-site symmetry. Okay, so now let's, that we have a bit of intuition, we can make our definitions a bit more precise. Dominic used this blend equivalence. I'll use this definition. For all of the examples that we know, they're the same. So our definition of equivalence for representations of a symmetry are 2 representations are equivalent if you can get between them by tensoring in with ancillas that carry an on-site representation of the symmetry, and applying a local unitary, a locality preserving unitary. So this is what we mean when we say that 2 representations are equivalent. And an on-siteable symmetry is a symmetry that is equivalent to the on-site representation. So this is just a product over all the local unitaries. Each of them is just supported on a single site. And what will also be important is the definition of quantum cellular automata. So there has been already a couple talks on QCAs in this conference and program, so I'll just be brief. It's just locality preserving unitaries modulo circuits. So, and circuits are just kind of built out of local gates up to some finite depth. In 1 plus 1D, these have been completely classified by a GMVW index given by the name of the authors on this paper. For 1 plus 1D QCA, they're classified by this index, which takes value in the rational numbers, P over Q. You can think of this as a generalized translation. So an example is P equals 2, Q equals 1, and that's just a translation of a qubit in the plus direction. If you do P equals 2, Q equals 3, that's translation of a qubit in the forward direction, and a 3-level system in the backwards direction, so a Q-chit. So it's just telling you about kind of the relative translation forward and backward. And I should mention that I did H2 of G with coefficients in Q star, so it's under, like, with multiplication. There's a explicit formula. Given an input locality preserving unitary, you can compute this guy, this index. These curly A's and curly B's are operator algebras of certain regions. You don't need to worry too much about this. It's just everything is well defined. There's a explicit formula for this index. Okay. So the index that we'll define for 2D symmetries is given as follows. We apply this UG for patch A, and then we also apply UH, and then UGH inverse. And so this operator will be supported on the boundary of A. This omega A GH is supported on the boundary of A. And we just define our index as the GMVW index of this locality preserving unitary. You can check that it's a 2-cocycle. It's a 2-cocycle just because of associativity of truncated symmetry operators. So if you have UG, UH, and UK, the fact that they're associative makes this a 2-cocycle. And the definition of equivalence is only up to a 2-co boundary. This is related to the ambiguity of how you truncate symmetry operators. So you can show that because you can truncate up to a locality preserving unitary in the boundary, that gives this ambiguity of a co-boundary. Okay, so now let's give a very, very simple example of G equals Z2 with a non-trivial omega. This simple example consists of a setting where we have these tau qubits on the vertices and these sigma qubits on the faces. So we have this hexagonal lattice, we have tau degrees of freedom and sigma degrees of freedom. And the symmetry operator takes a simple form. It's just a spin flip on all of the sigma degrees of freedom. And then this S takes as input a domain wall configuration of the sigmas and outputs an action on the taus. So this S is an operator that acts on the taus that is controlled on the sigmas. What does this do? It translates the taus in the counterclockwise direction with the up domain to the left. So it takes, for any kind of domain wall configurations of the sigmas, you can translate the taus in a clockwise direction with the up domain to the left. Okay, this symmetry is locality preserving. You can show that the symmetry, if you conjugate sigma z, sigma x, and any of the tau poly operators, it takes you to an operator that's supported in a finite range of that original operator. This OP is supported, so if this is P, it's supported not only on P, but also on the 6 plaquettes around P. And then this tau is, if is I, is supported on IJKL. So it's a locality preserving unitary. You can write down explicit expressions for these OPs and Fij. They're kind of ugly, but it works out. And we can calculate the index pretty easily. So for any configuration of the sigma spins, you can consider a boundary. So A is in this lower space of the black line. We polarize all the up spins, so the symmetry only acts below this line. If we act, so consider a domain wall configuration. If we act with the symmetry operator, we flip all of the spins below this black line, and then we also translate such that the up spins are to the left. Okay? And then when we act with the symmetry again, we translate with the up spins to the left. So you see on the boundary, there's a translation to the right by a single unit cell. If you do this carefully for all of the domain wall configurations of the sigmas, what you find is that U square restricted to a region, U restricted to a region square gives you a translation up to a finite depth circuit. So you can work this out explicitly, and this this has index 2, the other guys have 1. This gives you a non-trivial omega. Okay, even though this symmetry is, you can show that it's not on-site, and it's also quite easy to show it's not on-siteable. It has a trivially symmetric invertible state. The state is just a product state. You put all the sigmas into the plus state and all the taus into the up state. And you can show that the sigmas will be invariant under this product of sigma x. And then this S will translate the taus, but because they're all in the same state, the translation doesn't do anything. You can also construct a commuting parent Hamiltonian whose unique ground state is this product state. And each local term commutes with this symmetry operator. It's not obvious how to construct this commuting parent Hamiltonian if you do the naive thing, which is you just symmetrize with respect to the symmetry. So you have like sigma x plus sigma x conjugated by the symmetry. That's not commuting, but you use the magic of Wilbur-Shirley of constructing lattice models, and he comes up with this. So this PP is a local projector onto the tau z equals +1 along a plaquette. You can show that the projector onto tau z equals +1 everywhere is commutes with the symmetry. The problem is, how do we do a local projection? So there needs to be a dressing of this local guy that's given by this. So it's a local projection dressed by something. But roughly speaking, this projects into tau z equals +1 along this hexagon. And then this guy doesn't commute with the symmetry, but does so in the PP equals +1 subspace. So you can show that this is symmetric, it has a unique ground state, and each local term commutes with your symmetry. So it's very trivial in the sense that the ground state is as trivial as you can possibly want it to be as a commuting parent Hamiltonian. There is an interesting relationship between these non-onsiteable symmetries and GQCA in one higher dimension. So as I mentioned before, QCA are these locality-preserving unitaries modulo circuits. You can also define GQCA, which are locality-preserving unitaries that commute with the symmetry G, modulo circuits where each gate is G-symmetric. The simplest case is when this is not like a non-trivial as a QCA, but is protected by the symmetry. So what I mean to say is that it's a circuit that commutes with the symmetry as a whole, but it can't be broken into local symmetric pieces. So it can't be written such that each gate is symmetric. We're very familiar with these because SPT entanglers form a broad class of these kind of GQCAs. SPT entangler is a unitary that takes a state to a different SPT state. And because different SPT states are related by local unitaries, this is a local unitary, but they have to contain gates that break the symmetry because SPTs are protected by the symmetry. So SPT entanglers form a broad class of GQCA. In fact, for discrete symmetries, they're the only GQCA, as far as I am aware of, that we know. For U1 symmetry, there's a kind of richer story, 1 + 1D. And I won't go through all of the details. Is there a 5, 4? Okay. I won't go through all of the details, but there's a relationship between non-onsiteable or not gaugeable symmetries and GQCA in one higher dimension. So from this non-onsiteable symmetry, we can construct a GQCA in one higher dimension, and we can show that it's non-trivial. And so this gives us a class of G-protected QCA in 3 + 1D that are not SPT entanglers. You can also show that that gives you a class of G-Floquet phases, G-symmetric Floquet phases in 4 + 1D beyond SPT pumps. So a Floquet phase is a periodically driven system. And you can ask for periodically driven systems that respect to symmetry. And you can ask me more about it. But because of this non-onsiteable symmetry that's not related to any anomaly in 2 +.
Is this like anomaly in flow for like what I'm used to? This existence of the 1 +, and this is like it's going into the mapping torus. The second thing is like mapping torus, and the first thing is like anomaly in flow. Or?
Yeah. So for the case where this is an anomaly, that's the usual relationship between anomaly and flow, in the sense that there's say a 3D SPT entangler related to a 3D SPT. And then this non-onsiteable symmetry is the 2D anomaly, 2 + 1D anomaly. Mm-hmm. But here, none of them are related to SPTs and anomalies of the usual sense. But on the lattice, there's still this non-onsiteable property that, does that answer your question?
Okay. No, it's all right. I just wanted to know if I was following. Yeah. So
in the usual case of anomaly, it is a subset of this, basically. Okay, and then again, that would be related to also Floquet phases in 1 dimension higher that pump SPTs to the boundary. How does all of this relate to gauging? So before you even talk about dynamical gauging, let's talk about coupling to background gauge fields and defect Hamiltonians. So for these kinds of symmetries, there's already an obstruction at the level of defect Hamiltonians. To understand defect Hamiltonians, we can construct a defect Hamiltonian with a defect on this line gamma. You can think of this UG as acting on the left half space. And so it inserts a defect, G defect along gamma. And the important thing about these G defects is that you can move them with local unitaries. So if I act in this region A, I can, with the restricted symmetry operator to A, I can move this G defect from gamma to gamma prime. And the second important property of these defects is that you can fuse them. So if I have two defects at G and H, I can fuse them with this local unitary operator lambda. So the important thing about defects is that you can move them and fuse them. And you can already kind of see that there's a problem here. So suppose that we had, for our Z2 symmetry, this is G and this is also G. And we move this G defect along, and then eventually we fuse it to get this defect configuration. This defect fusion operator lambda looks like our omega restricted to a region, right? Because it has a UG here and a UG here and an identity here. But this lambda is supported on a finite patch. So that means that this omega would have to be truncatable. But if omega is a translation, you can't truncate a translation. So then this little omega, this cocycle, must be trivial. So there's already an obstruction at the level of trying to couple to background gauge fields and have consistent kind of defect Hamiltonian. Yeah.
Can you elaborate on this more? Because in the local field theory case, we would have said that this means you don't have the symmetry.
Uh-huh.
Right? We would have said that having the symmetry defects is equivalent to coupling to background fields.
Uh-huh.
So it would be great if you could unpack this slide a little more.
Yeah, so all I meant was the defect configuration, how to get that defect configuration should only depend locally on the gauge background configuration of the background gauge field. Here, it looks like an identity operator. And here, it looks like G, and here it looks like G. And so if you want to fuse this guy to the right-hand side, the configuration of, so you bring this G along. This guy looks the same as here, and this H looks the same as here. So these two, so basically the, yeah, maybe I can. Write it out. So we said that H gamma G is equal to like this U less than gamma, H not U less than gamma. G. Yeah? Do you agree with this? Okay. So now we have a UG for this configuration. And we have a UG for this configuration. And then we have a UG for this configuration. And so in particular, UG for this configuration is basically the symmetry operator on this right-hand side. So let's call this U less than gamma G. And then this is U less than gamma prime H. And then this is U less than gamma double prime of GH. Let's call these operators for these different defect configurations. These. And we can see that UG less than gamma, UH less than gamma prime, this is equal to lambda. And this lambda is only supported along here. So this lambda ends. But if this guy depends only on the local defect gauge field configuration, then this should be a translation that just ends.
Are you sure it doesn't mean you haven't misidentified the symmetry algebra?
You could ask, what if I define this UGH gamma double prime as basically just product of these two? Then you would have a translation along here that kind of splits into these two. Then this lambda is trivial, but then you identify the trivial defect with a translation along here. And you kind of want this property, U trivial, to be equal to H trivial to B. So it's incompatible with wanting these operators to depend locally on the gauge field configuration, and also for this to be true, because then you'll just be translating this like anywhere along your system.
Make a comment. So does.
Sorry? So if you just take the bulk symmetry operators, it's just like a Z2 symmetry. Yeah, so if you restrict it to a patch, then it squares to a translation on the boundary of that patch.
So if I work in space with some periodic boundary conditions,
Yes.
what happens?
If you have periodic boundary conditions, all you see is a Z2 operator. Does that answer?
So in what sense does it mix with translations?
If you take, yeah, if you restrict this operator, so it's not acting everywhere on periodic boundary conditions, then it squares to a translation on the boundary, a 1D translation. But on periodic boundary conditions, yeah, it would just look like a Z2 fusion.
I see. So if I have a defect, the translation starts playing a role, but without defect, it doesn't.
Sorry?
It's a question. If I don't have any defect, I don't see the translation, but on a defect, it acts as a translation. Yeah. So it is as if in the twisted Hilbert space, the algebra is mixed with translation. So I could ask, so what is the symmetry algebra on the defect Hilbert space if I have only one defect?
Then it would also have this kind of Z, I guess. Translation.
What?
Then there would also be the Z of translation.
So in the twisted Hilbert space, which makes sense, U square is translation? Is that the statement?
So in the twisted Hilbert space, in the sense that we insert a single symmetry defect, and then we can act with the symmetry everywhere in the presence of that single symmetry defect. But then if you act with the symmetry everywhere, I don't think you would see the the translation on the single symmetry defect. So.
Okay, I'll reverse the question.
Yeah.
What should I see? How will I see the fact that it mixes in translations in a configuration of defects without restricting the range of where the symmetry acts?
I don't know if you can get the mixing with translation without restricting the symmetry action.
Okay, thank you.
Yeah, so can you go back to picture of this Z2 domain walls? Well, I was a bit confused about this. Let's say we have a Z2 symmetry.
Yeah.
And so we have some wave function with a Z2 a configuration of Z2 domain walls, and then we can, I guess we can always realize this defect configuration of Z2 domain walls by acting the symmetry operator on let's say we have a plus and minus domains, and we can always declare to act like a symmetry operator on the plus region. Then we just have a configuration of defect without the issue about this lambda flows on the transparent inside some single domains. Sorry for being a bit technical, but I was a bit confused why you are worrying about this issue, and I thought that there is always some a way to create symmetry defects without worrying about this lambda issue. Is that right?
You can create individual symmetry defects, but then you want to be able to create symmetry defects in a consistent way that obeys the fusion and movement properties that you would want from symmetry defects.
Do you think it? Okay, I see. Yeah, let me think more about it. Yeah, okay.
So I just wanted to add a clarification about the previous question. I think it's fine to like create a configuration of defects in the ground state, which I think is what the question was. But I mean, this issue is not a question about just creating the defects in the ground state. You want to like create it like in the like whole like Hilbert space, I think.
All right. So if you had an individual state, then it could be that the symmetry operators can act consistently on that state. But as an operator algebra, it doesn't form this kind of, and if you consider all of the states.
I think in the interest of time, we should let the speaker continue, and we can reserve questions for the end.
Okay. So this is basically the end. So if you work a bit harder, you can show that there's more involved proof that shows that if you want to have consistent set of local Gauss laws, so for Z2 symmetries, you might want local Gauss laws that each commute with each other, then that's incompatible with a non-trivial omega. So for dynamical gauging, if you want commuting local Gauss laws for your Z2 symmetry, you basically need this omega to vanish. We have also construction for more general H2 classes, and then also some simple fermionic examples that are related to this, thank you, Chern pump, which I can talk more about offline, but they're also fermionic analogs of basically what I talk about. There's some interesting questions. One is also if there are nice examples we can write down in higher dimensions. We only looked at 2 plus 1D because that was the simplest setting we could find. What are the physical consequences of these kind of non-onsiteable yet trivial symmetries? And then is there an analog for non-invertible symmetry? So I kind of focus on the most vanilla example where everything's invertible, finite. But recently there's been work by Corey Jones and other people about QCA in the context of these anion chains. Maybe they can be leveraged to have non-invertible examples. Thank you, that's all I have.
Thanks for the nice talk. So I have a question. If you allow infinite dimensional ancillas, can't you gauge these symmetries?
Yeah, so if you allow infinite dimensional ancillas, then this GMVW index isn't even super well defined. I would assume in that case, things might go through, yeah.
So they, in some sense, they are physically gaugeable and anomaly free. So.
Yeah, that's why I put the caveat in the very beginning that we consider equivalence with finite dimensional.
So with finite dimensional, the space we cannot gauge.
Yes, yeah.
So about the fermionic construction, I guess instead of translation, I could think of pumping a Majorana mode, and that seems to be similar to like some Z2 fermionic SPT that Lucas constructed. I was wondering if you can comment about that.
Yeah, so there actually the non-trivial class starts at like Z4, because you basically always have to maintain the fermion parity subgroup. So there we have kind of non-trivial, non-onsiteable Z4 or even Zn greater than equal to 4 in 2 plus 1D. That would not be kind of what you were talking about, because you would be talking about the n equals 2 case. Is that correct?
Yeah, it's more like an SPT entangler for the root Z2 fermionic SPT. Like the Majorana chain decorated domain wall.
So that would be a Z2 times Z2F, right?
Yes, yes.
But not just Z2F, or?
Right, not just Z2F.
Yeah, so, yeah, in this case, it would be like a Z4F kind of non-onsiteable symmetry. So it's a bit different from like a Zn times Z2F.
Yes.
Yeah. And there's no non-trivial Z4F. There's no Z4F anomaly in 2 plus 1D. So, and if it was an SPT entangler, it would also be not an anomaly, right? The anomaly would be in one lower dimension.
So in 1+1D, the equivalence between the obstruction to gauging and the obstruction to trivially gapped face is related to the fact that the Lagrangian algebra of the SymTFT are all connected by gauging. So in this case, is this related to, I'm not sure whether it's a factor or not. If I consider a 3+1 dimensional SymTFT, some topological boundary conditions are not connected by gauging.
So I think that it's a bit different because when people work with symmetry TFTs, they're really looking at kind of IR field theories. And these are not really anomalies in the space of ground states. They're really anomalies in kind of the space of unitary operators when you include the entire spectrum. So from the symmetry TFT, I would say that in the lattice model, for example, Sahan and Wilber's work would show that those two definitions were equivalent. It required more work than just using symmetry TFT. And the way that they did it was by just constructing a disentangler when there's no anomaly in terms of gauging. And the reason why it's different in 2+1D is just that there are indices and obstructions that occur in higher dimensions that are not there in 1+1D. Does that answer your question?
Yeah, more or less, yes. Thanks.
Yeah, I don't know if there's like a nice way to think about this in terms of symmetry TFT. That's an interesting question.
Thanks for the nice talk. Yeah, just a naive question, but I'm wondering if it can be understood as some analog of the symmetric fractionalization, in the sense that you have it sounds like you have if you have a junction of the zero-form symmetry defects, the junction supports some QCA index. And so do you think that this, you have this QCA index, it's a flow around this some codimension 1 defect? Is it a symmetry of the theory or not? If it's a symmetry, I really regard this as a symmetry fractionalization. Well, is it correct?
Symmetry fractionalization, I usually think of in terms of anion theories. But you can think of it as a decorated domain. Well, is that what you're going to say?
I was just going to say that this is exactly the equation you would use to define the extension of the symmetry.
Yeah, you can roughly think of it as extending by translation.
It's not a one-form symmetry.
Yeah.
So it is not a symmetry.
You can just extend the zero-form symmetry by projectively. It doesn't matter if it's a one-form symmetry. And that's the word we use for symmetry fractionalization, but if you have a central extension, this is where you would detect it. So, I mean, that's why I was saying, are you sure you haven't sort of misidentified the symmetry? In the sense that if that's the defining equation for the symmetry, then it's not Z2.
Can I comment to Clay's question? So in this case, I think the defect Hilbert space exists, but Carolyn is saying that there is a one preferred presentation of the defect Hamiltonian, and which is for GH. Another presentation is that when you put a G defect and an H defect. So the obstruction here is to fusing them, which is like a gauge transformation in the continuum. So you have the symmetry, you have all the symmetry defect, but you have different presentation of same symmetry defect. Is that?
Yeah.
Right? So it's kind of a gauge transformation.
So following up on this comment by Clay, should we think of extending this zero-form symmetry, so 2-vec G by these QCAs somehow in this case, and then maybe you could reformulate the conditions of existence of fiber functors and so on, and with that larger symmetry or that modified symmetry, and then maybe these two definitions would again agree.
Yeah, I think that if you, I don't know how to carefully include that within the entire framework of the categorical data, but there might be a way to consistently include that.
The thing in the continuum, sort of just looking at fusion 2 categories and their centers and the existence of fiber functors and the non-gaugeability, those things in the continuum seem to agree still. But here you're actually adding some additional QCA data that is not contained there.
Yeah, in the sense that in the continuum, the translation is kind of trivial. Yeah.
I just want to ask about this. You said it's non-gaugeable. Did you assume that you preserve translation symmetries?
Here, like in the sense of coupling the background gauge field, it was this like inconsistency of trying to do the gauge transformations. I don't think we assumed other symmetries beyond that.
So it's not like there's a way to gauge it, but that gauging breaks the translations.
Yeah, so like another way to say is like the only assumption that we had for dynamical gauging is that if you have a Z2 symmetry, your Gauss laws should commute with each other, and they should be local. And then there's some other properties of how they, if you take the product of all the Gauss laws, then its action on operators on the matter fields in the zero flux sector should be equal to the symmetry action on them. So if you take those like as your basis assumptions, then you'll find an inconsistency if there's a non-trivial omega.
Okay, thanks.
Yeah, I just wanted to make a comment about the symmetry fractionalization comparison. If I have a Z2 symmetry in a TO, and I take the Z2 operator and I truncate it and I square it, oftentimes the symmetry fractionalization will manifest by the or some loop operator appearing on the boundary of that.
Yeah.
So that's like a purely operator way to state the comparison people are making with the defect. So it really does have that flavor.
Yeah, that's why I said I also kind of think of it as like an extension in that way, but yeah, so you can view it that way, I think.
Yeah, but if there is some extension, then usually when you insert defects, you want to know the entire symmetry, including all the extension data before you insert the defects. So maybe the defects aren't being inserted in the right way or something.
I see. So you're saying that there's like maybe a different condition on the fusion of the defects that we might insist that takes into consideration the extension data, and then under that way is like consistent to insert background gauge fields and maybe even couple and make them dynamical.
I don't know about the making them dynamical part. That's another step, but at least up to that point, yeah.
Yeah, that's interesting. Yeah.
Maybe you said that and I missed it. How did you construct the defect for this system?
So, for example, this G defect would just be acting on the left half space with the symmetry operator.
Right, but when you say that you act on half space, you said that it involves translation.
I said that the fusion of the defects involved translation.
Well, so I'll take two of them, and then I fuse.
Yes.
Then what does that mean?
If
I just fuse the defect, I'm not, I don't want to act with the symmetry, so I just created the defect the way you did, and then I create another one the way you did, and I fuse them.
Yes.
So what do I get? I get a defect for translation?
Yes.
What does that mean?
So what I drew here is if you literally fuse these together, then this line will carry a translation. But then this is not really what you want for the end of the identity operator. So that's kind of...
I don't even understand the sentence. What does it mean that it carries translation?
Meaning any kind of tau spin on this line would get translated.
Along the line?
There's like a literal translation operator along this line.
So if I look at the Hamiltonian, what does it look like?
Then there will be a translation action on the Hamiltonian terms along this line. And then it kind of splits off. There's a bulk symmetry action here. For some states, it gets translated this direction. Some states, it gets translated this direction. And along this line, there's like just a translation of a unit cell.
So what happens to the lattice there?
Sorry?
So what happens to the degrees of freedom on the lattice? There's a term in the Hamiltonian that implements that.
Yeah, so all of the spins that lie on this line will get translated upward.
And what happens at the end?
Then some states get translated to the right, some to the left. There's a bulk symmetry action here because there's Z2. When you fuse them, then there's like a G action here. Because of Z2, this will be identity. So then if you follow carefully, some states will go to the right, some states will go to the left. Attached to the symmetry action.
So if I just look at the spins and I apply this, what does the Hamiltonian look like? Is a spin from here times spin from there? What kind of terms are there?
So when you try to, so now what you do is you have this. Maybe I want to change the order.
Maybe it would help that people in the back cannot see. Thank you.
G. And then what you want to do is you act with some lambda. Right? This is kind of what you want. So you have the H, you have the G, and then you fuse them together. And then what this will do is it will lead to a translation of the Hamiltonian terms that are supported on this line in the upward direction. Does that make sense?
Maybe. I'll ask you later.
Okay.
Okay, maybe let's just do one more question. When you define your defects, usually you're allowed to like decorate the like the boundary.
Yeah.
Is there any what kind of decorations are allowed? Like, can you decorate with a QCA or?
You can, but that will sort of only change this co-boundary. It won't change the actual co-section.
I see. Cool. Thank you.
Okay, let's thank our speaker one last time.